Welcome to 8.2, solving systems of linear equations in two variables using the substitution method. So in the last section, we used the graphic method, and we were finding the intersection point of the two lines. And that's a good method, although it kind of breaks down if you draw a bad graph or if you have like fractional answers as your solutions to that, because it's hard to see those on the graph. So this is the first, excuse me, of the two algebraic methods that we'll be looking to do this. And there's a little how-to right here, but I'll talk about these things in the context of the problem. So this is the property, we're using the property of substitution. That is the substitution method to do this. So if we look at this first one here, notice the first equation we have x equals 8 minus 4y. So now because x equals 8 minus 4y, in the second equation right here, wherever we see an x, we can write 8 minus 4y because they're equal. So we can really rewrite this first one as 3 times 8 minus 4y plus our 5y equals 3. Now notice, the only thing I've really done is replace this 8 minus 4y and for that x right there. So now what we have is we have a linear equation in one variable, so we can solve this for y. So distribution here, 3 times our 8 is 24. 3 times our negative 4y is negative 12y. Plus 5y equals 3. Combine our like terms, so we have 24. Negative 12y plus 5y is negative 7y equals 3. Get rid of our 24, solving for this y, so subtract 24 from both sides. And we'll come back up here. So on this side we get our negative 7y. 3 minus 24 is negative 21. Divide by negative 7, and we get y equals 3. So what that does is that gives us the y coordinate. So we know the solution of this is going to be something comma 3. Now, they also call this the method of substitution because once we have our y, we can take that, plug it back in this equation that we have solved for x. So plug that into the y right there and solve for x. So plugging that back into our first equation here, x equals 8 minus 4 times y, so we plug our 3 in for y. So we get x equals 8 minus 12, or x equals negative 4. So negative 4, 3, this is the solution. Now if we wanted to check the solution, we could plug the x in for the x and the y in for y into both these equations and make sure we have a true statement. That's something that I'd recommend you doing for the examinations and things like that. I'm not going to do that for this one exactly right here. So notice the first one we had an equation that is specifically this was already solved for x. In the second one, neither of these is solved for a variable, but it wouldn't be very hard to look at this first one and take this first equation right here and solve that right there for y. So let's go ahead and do that. So if we solve this first equation for y, let me draw a line here, we add x to both sides, so we get y equals x plus 5. Okay, so we've just taken this first one, added x to both sides, it's canceled the x on the left, and we have the x on the right now. Okay, so now since I've solved this for y, wherever I see a y in the second equation right here, I can plug in x plus 5, because these two things are equal. So we have 2x minus 2 times x plus 5 equals 10. We've solved this. So we have this equation right here that just has our single variable x. So we want to go ahead and solve this. So we're going to do our distribution here. So we have our 2x, negative 2 times x is minus 2x, negative 2 times 5 is minus 10, equals 10. Combine our like terms. 2x minus x is 0, so these cancel, and we get negative 10 equals 10. Well, negative 10 does not equal 10. So really what this tells us a couple things. As soon as the variables go, it's going to be one of two scenarios. That is, if we're thinking about this graphically, we could have two parallel lines, or we could have essentially two lines that are in fact the same line. That's what happens. On the first one, when we end up with y equals 3, this gives us a y value, we get this. Now, the variables went away here, they canceled out. So this is one of these two things. Now, what differentiates this is this. Is negative 10 equal to 10? No, it's not. Which means that essentially these two lines are parallel, though we have a situation like this, and there is no solution. So, negative 10 doesn't equal 10, so we have no solutions. If we would have got something like 5 equals 5, something that's true, that would be a scenario like that, and there's an infinite number of solutions. So once again, if we have no solutions, the system is said to be inconsistent, and it's independent. So that's how we did this. This one up here, because we have a solution, is consistent and independent. So just brushing up on some of the terminology right there. So when the variables go away, it's one of these two cases. And if we have something like this, that's when we have something that's definitely not equal. That's giving us no solutions. If we have something like this, that comes from a 5 equals 5 or something that's clearly true, and that would give us an infinite number of solutions. So moving on to this last problem, we're going to look at this. Now notice, neither of those is solved for P nor Q. So we need to take one of these equations and solve for either P or Q. Now, if we just analyze this really quickly, and we think about it, like if we're solving the first equation right here for P, we're going to have to divide by 4. And if we divide 2 by 4, we're going to have fractions. If we solve this first equation for Q, we're going to divide everything by 2. Well, 4 is divisible by 2 and 16 is divisible by 2. So we want to solve this for Q. If we look at the second one, if we solve for P, we'd have to divide by 5. That's not going to look so good. If we solve for Q, we have to divide by 7. That's pretty much even worse. So you want to like spend a couple minutes just thinking about, or maybe like 30 seconds thinking about what's the easiest variable to solve for when you're using this method of substitution. So looking at this first equation, 4p minus 2q equals 16, we're going to solve this for q. So I'm going to subtract 4p's. These cancel, we get negative 2q equals negative 4p plus 16. Divide everything by negative 2. And we get q equals 2p minus 8. So I'm going to go ahead and box that up. Now, when we do our substitution, we have to put this into the other equation. Because we used the first equation to solve this, we're going to substitute this in for the q, where we see it right there. So I'll go ahead and write that over here. So plugging that in, we still have our 5p plus 7 times plugging this right in there for our q. We have a 2p minus 8 equals 1. So now we have an equation in just p. So this kind of goes back to like the things that we did in the second module, module number 7, you know. And same thing with the last, this no solutions and infinite solutions. That's the same as it was back in that. So here we have our 5p, our 7 times 2p is 14p, 7 times 8 is 56, equals 1. Okay. So we have that. So now we want to combine like terms on the individual sides. 5 plus 14 is going to give us 19p, and then we have minus 56 equals 1. Add 56 to both sides. Here we get cancellation, so we get 19p equals 57. Divide by 19, and we get p equals 3. Okay, so we have our p equals 3. So in this ordered pair right here, because it's p, we have these pq combinations, we know that it's going to be 3, comma, whatever q is going to be here. Now, in order to get q, they call this the method of substitution, because we're going to do some substitution here. In fact, this equation's already solved for q, so if we plug our p back into here, that is going to help us solve for q. So plugging it back in here, we get q equals 2 times 3 minus 8. So we get q equals 6 minus 8, so q equals negative 2. So 3, negative 2, that's our solution. And we can always plug these coordinates back into the original equation up here to make sure that we got the right answer. Feeling pretty good about those, so that essentially is the method of substitution. So we'll see you next time.